Okay, welcome to a quick overview of the Spheroid aerodynamics package developed in Unity. If you open up the file, this is what you should see. So this is in the editor window, and we're staying in the editor window all the way through because most of the interaction happens via an editor script on this lifting body object. If you come in, and the first thing to do is make sure that body is selected, and then you can see all the gizmos on it. So this orange thing is our aerodynamic body. It's got a forward direction, a left direction, and an up direction. So this Z forwards is our convention in Unity. So we're using a standard left-handed coordinate system. Z forward, X is left, Y is up. Okay, and we've got some controls on our body, so we can control the aspect ratio, so we can sort of to make it more blobby or slender. We can control the thickness. So that's a thin plate, and that's a fat plate, and we can also control the camber, which you can only really see sideways on, but the camber is adds a bend to the plate. So if we make it slightly thicker and change the camber. Okay, I mean visually actually you can't see a lot. Aerodynamically obviously camber makes a difference in that it changes the zero lift pitching moment and it changes the zero lift angle. Anyway, so you can play with the shape that way, and then these gizmos here, this varies the angle of attack. So the pink is the lift vector and the red is the drag. So the model updates dynamically in the background. So at 0 angle of attack, we've just got, let me just make it a bit thicker so we've got a bit more drag. We've just got drag, but then we increase it, we've got lift, and then it stalls and it comes down. And then eventually when we're at 90 degrees angle of attack, you've got no lift and just drag, which is the kind of behaviour you'd expect. And then we've also got the side slip angle, which is the green one there, so we can change the angle which the wind comes from. As we do that, you notice this sort of transparent body appears. And what we've called this is the equivalent aerodynamic body. So when the wind is coming from this way, what we're doing is we're approximating this wing or this body as we take the sort of plane through the center of there, and we approximate it with a body with the same thickness to chord ratio, or same thickness ratio, and the same aspect ratio. And what it means there is that we can then calculate all the aerodynamic properties at an arbitrary angle, and that works all the way to going to 90 degrees side slip, in which case the body is identical to what is the equivalent body is the same as the other one, because the wind's just going straight down to one side. So what that means is whichever way the wind is coming from, we get an approximation to that, which we can then apply some aerodynamics to. So the approximation is kind of geometrically makes sense, and it makes sense aerodynamically, apart from, of course, it strips out any sweep effects. So we're not model assuming that. It's a body with the same effective thickness and aspect ratio. So our kind of lift curves are correct, but of course it doesn't model anything to do with separated flow on swept wings and the like. But that's okay. It just means our body behaves itself sensibly as you go from 0 to 90 degrees side slip angle. Okay, and then if you now go into play mode, and it jumps straight stays in the scene mode when we do that. There's a live graph plotted behind. I couldn't get that working in edit mode. It didn't really make sense to do it anyway. So what it now does is now calculating for the full range of side slip angles. So actually the side slip thing, it doesn't make any difference. Oh yes, it does actually. Anyway, so what it's doing is as you vary the angle of attack, that red blob shows what's going on. So for each of those side slip angles, it recalculates the model and shows it here. And then just to kind of verify things are working, if we increase the aspect ratio, the lift curve slope goes up to a limit. Then we decrease it, the lift curve slope comes down, and eventually goes a bit weird. and then if we increase the thickness ratio, okay, what's it doing? Mark. Eventually, if we make it thick enough, it just turns into a blob, and we can see there it's now just a body with drag. There's a tiny bit of residual lift, but it's mainly just drag. And if we change the aspect ratio, it doesn't make a lot of difference just because it's a blob. If we bring that thickness ratio down, it now starts becoming a wing again, and we're back to kind of normal aerodynamics. If you notice on here, there's the linear part, which is the bit between sort of positive and negative stall, and there's the non-linear bit, the post-stall bit, which is kind of sine 2 alpha bit. And they're two separate models, and the stall angle is sort of an empirical relationship where it just sort of based on thickness and on aspect ratio, it chooses where to jump between the two, and it does a little bit of blending, so you get kind of a smooth variation between the two. The pitching moment is just applied in the sort of pre-stall bit of the aerodynamics. Once the thing is stalled, the pitching moment is assumed to all come from the lift, and so this kind of the zero lift pitching moment component just drops off to 0. Okay, and just to check some other things, if we introduce some camber, what you can see is that kind of shifts it to the right. So that's actually negative camber, positive camber, and that's negative camber, shifts it the other way. So in terms of setting up an aerofoil or something, you can set the camber on it to get your CM0 and alpha 0 correct. Okay, so I think that's a sort of brief summary of what this can do. In the kind of Word doc, there's some stuff of what the theory is, and this particular model was really developed just for debugging purposes. There is an Excel model of it, but this was kind of useful just to make sure that it kind of behaved itself on all the different kind of extremes, but it's kind of useful exercise in making a user interface for a model. Okay, thanks for watching.